Section 9.1, Reactions and Equations. The objectives of this lesson are to recognize evidence of chemical change, represent chemical reactions with equations, and balance chemical equations. Some vocabulary to review will be chemical change, and new vocabulary we'll come across is chemical reaction, reactant, product, chemical equation, and coefficient. Do you know that the foods you eat, the fibers in your clothes, and the plastic in your CDs have something in common? Foods, fibers, and plastics are produced when atoms and substances are rearranged to form different substances. The process by which the atoms of one or more substances are rearranged to form different substances is called a chemical reaction. A chemical reaction is another name for a chemical change, which you've read about in Chapter 3. Chemical reactions affect every part of your life. They break down your food, produce the energy we need to live. Chemical reactions in the engines of our car and buses provide energy to power the vehicles. They produce natural fibers such as cotton and wool in plants and animals. In factories, they produce synthetic fibers such as nylon. How can you tell when a chemical reaction is taking place? Although some chemical reactions are hard to detect, many reactions provide physical evidence that they have occurred. A temperature change can indicate a chemical reaction. Many reactions, such as those that occur during the burning of wood, may release energy in the form of heat and light. Other chemical reactions absorb heat. In addition to temperature change, other types of evidence might indicate that a chemical reaction has occurred. One indication of a chemical reaction is a color change. For example, you might have noticed that the color of some nails that are left outside changes from silver to orange-brown in a short time. The color change is evidence that a chemical reaction occurred between the iron in the nail and the oxygen in the air. A banana changing from green to yellow is another example of color change, indicating that a chemical reaction has occurred. Odor, gas bubbles, and the appearance of a solid are also indications of chemical change. Chemists use statements called equations to represent chemical reactions. Equations show a reaction's reactants, which are the starting substances, and products, which are the substances formed during the reaction. Chemical equations do not express numerical equalities as mathematical equations do, because during chemical reactions, the reactants are used up as the products are formed. Instead, the equations used by chemists show the direction in which the reaction progresses. Therefore, an arrow rather than an equal sign is used to separate the reactants from the products. You read the arrow as react to produce or yield. The reactants are written to the left of the arrow and the products are written to the right of the arrow. When there are two or more reactants or two or more products, a plus sign separates each reactant or each product. The elements of equation notation are shown below. Reactant 1 plus reactant 2, react to produce or yield product 1 and product 2. In equations, symbols are used to show the physical states of the reactants and products. Reactants and products can exist as solids, liquids, and gases. When they are dissolved in water, they are said to be aqueous. It is important to show the physical states of reactions, reactants, and products in an equation because the physical state provides clues about how the reaction occurs. And Table 9.1 shows some of those basic symbols that we'll come across. You have your plus sign, your unidirectional arrow, your bidirectional arrow, and then you have the states of matter in parentheses, solid, liquid, gas, or something that is aqueous. You can use statements called word equations to indicate the reactants and products of chemical reactions. The word equation below describes the reaction between aluminum and bromine, which is shown in Figure 9.3. Aluminum is a solid and bromine is a liquid. The brownish red cloud in the photograph is excess bromine. The reaction's products, which is solid particles of aluminum bromide, settle on the bottom of the beaker. So aluminum plus liquid bromine gives a solid aluminum bromide. The word equation reads aluminum and bromine reacts to produce aluminum bromide. Although word equations help to describe chemical equations, they lack important information. A skeleton equation uses chemical formulas rather than words to identify the reactants and products. For example, the skeleton equation for the reaction between aluminum and bromine uses the formulas of aluminum, bromine, and aluminum bromide in place of words. Right? Al with an S symbol, solid symbol, plus Br2 with a liquid symbol with that unidirectional arrow gives aluminum bromide in the solid form. How could you write the skeleton equation that describes the reaction between carbon and sulfur to form carbon sulfide? Carbon and sulfur are solids. First, write the chemical formulas for the reactants to the left of the arrow. Then separate the reactants with a plus sign and indicate their physical states. Finally, write down the chemical formula for the product, liquid carbon disulfide, to the right of the arrow and indicate its physical state. The resultant is the skeleton equation for the reaction. The skeleton equation tells us that carbon is in the solid state, reacts with sulfur in the solid state to produce carbon disulfide in the liquid state. Like word equations, skeleton equations lack some information about reactions. Recall from Chapter 3 that the law of conservation of mass states that in a chemical change, matter is neither created nor destroyed. Chemical equations must show that matter is conserved during a reaction. Skeleton equations lack that information. If we look at Figure 9.4, the skeleton equation for the reaction between aluminum and bromine shows that one aluminum atom and two bromine atoms react to produce a substance containing one aluminum atom and three bromine atoms. Was a bromine atom created in the reaction? Atoms are not created in chemical reactions, and to accurately show what happens, more information is needed. To accurately represent a chemical reaction by an equation, the equation must show equal numbers of atoms of each reactant and each product on both sides of the arrow. Such an equation is called a balanced chemical equation. A chemical equation is a statement that uses chemical formulas to show the identities of relative amounts of the substances involved in a chemical reaction. The balanced equation for the reaction between aluminum and bromine is shown in Figure 9.5, and this reflects the law of conservation of mass. To balance an equation, you must find the correct coefficients for the chemical formulas in the skeleton equation. A coefficient in a chemical equation is the number written in front of a reactant or product. Coefficients are usually whole numbers and are not usually written in values of 1. The coefficient in a balanced equation describes the lowest whole number ratio of all the amounts of the reactants of the products. So if we look at aluminum and bromine gas, we can go ahead and balance that out so that we start with 2 aluminum atoms and 6 bromine atoms, so that we also end up with 2 aluminum atoms and 6 bromine atoms. And to do this, our coefficients would be 2, 3, 2. Most chemical equations can be balanced by following the steps given below. For example, you can use the steps to write chemical equations for the reaction between hydrogen and chlorine that produce hydrogen chloride. So step 1 is to write the skeleton equation for the reaction. We have H2 gas plus Cl2 gas yielding HCl gas. Then we're going to go ahead and count the number of atoms in the reactants, and we're going to go ahead and count the number of atoms in the products. So we have 2 hydrogen atoms and 2 chlorine atoms in the reactants, and 1 hydrogen atom and 1 chlorine atom in our products. Now we're going to go ahead and change the coefficients to make the number of atoms on each element equal on both sides of the equation. Right, so to do that, because we have 2 hydrogens and 2 chlorines on our reactants, but 1 hydrogen and 1 chlorine on our product, the best thing to do is to put a 2 in front of the HCl so that we end up with 2 hydrogen atoms and 2 chlorine atoms on our product. Then we're going to go ahead and look at this and make sure that we write our coefficients in the lowest possible ratio, right, so that we have a 1, 1, 2. And always just go back and check your work to make sure that the chemical formulas are written correctly and that your equation is written in the lowest possible ratio. Writing a balanced chemical equation. Write the balanced chemical equation for the reaction in which aqueous sodium hydroxide and aqueous calcium bromide react to produce solid calcium hydroxide and aqueous sodium bromide. And the first thing you're going to want to do is you're given the reactants and the products, so you're going to go ahead and create yourself a skeleton equation. Once you have your skeleton equation written out, right, NaOH, aqueous, plus CaBr2, aqueous. Then you have your arrow creating calcium hydroxide, CaOH2, in the solid form, and then NaBr in the aqueous form. We should go ahead and count out how many atoms do we have on each side. A little trick I like to do is that if I notice that the polyatomic in the reactants also shows up as a polyatomic as a product, I usually just go ahead and clump them together. Saves you a lot of time in counting individual atoms, and it makes for balancing much easier. Okay. So now that we go ahead and do this, we notice that we have 1 hydroxide on your reactant side, but 2 hydroxides on your product side. So what I would go ahead and do is put a 2 in front of the sodium hydroxide to go ahead and balance out my hydroxides. But in doing so, now I have 2 sodiums as a reactant and only 1 sodium as a product. Now I notice that my sodium on my product side is attached to the bromine, but bromine on my reactant side, I notice I have 2. So if I put a 2 in front of the sodium bromide, right, not only does that balance out my sodiums, but that also balances out my bromides. So it gives me the ratio of coefficients of a 2, 1, 1, 2. And again, if we go back and add them all up, we can go ahead and check our work. We got 2 sodiums on each side. You got 2 oxygens, 2 hydrogens, a calcium, as well as 2 bromides showing up on both sides. So how about you take a couple minutes, and why don't you try 4 and 5 of the practice problems. Here are your word equations written out and balanced. Probably the most fundamental concept of chemistry is the law of conservation of mass that you first encountered in Chapter 3. All chemical reactions obey the law that matter is neither created nor destroyed. Therefore, it is also fundamental that the equations that represent chemical reactions It includes sufficient information to show that the reaction obeys the law of conservation of mass. You have learned how to show this relationship with balancing chemical equations. The flow chart above in figure 9.6 summarizes the steps for balancing equations. You will probably find that some chemical equations can be balanced easily, whereas others are more difficult to balance. All chemical equations, however, can be balanced by the process you learned in this section. Section summary of 9.1. Some physical changes are evidence that indicate a chemical reaction has occurred. Word equations and skeleton equations provide important information about a chemical reaction. A chemical equation gives the identities and relative amounts of the reactants and products that are involved in chemical reaction. And balancing an equation involves adjusting the coefficients until the number of atoms of each element is equal on both sides of the equation.